All right. So we're going to take care of chapter 15 today. And even though the title of the chapter is acid-base equilibrium, we're basically talking about buffers. So a few things that we need to get out of the way before we get to the subject of buffers proper. It's the concept of the common ion effect. And this is a direct result of Le Chatelier's principle, which you recall states that if a system is at equilibrium and we do something to disturb the system will respond in such a way as to reduce the effect of that disturbance. So if we have an acid-base situation, and we shift the equilibrium by adding an ion that is common to the balanced equation, then there will be a shift in the equilibrium to compensate for that addition. The flip side of that is that if we add something to the system that has absolutely nothing to do with the balanced equilibrium equation, then there's no effect. That's the common ion effect, and the absence of the common ion effect in the latter example. So here's a practical example. Say we have hydrocyanic acid, and it's in solution reacting with water, and it will produce some hydronium ions and the conjugate base of the HCN, which is CN minus. So if we add sodium cyanide to that mixture, let's just put it up here on the board so I can talk with my fingers. Okay, so there's our equilibrium situation. And if we add sodium cyanide to that mixture, what ion are we adding? What ions, as a matter of fact, are we adding? So if it's aqueous, then it's going to produce, and this is completely soluble, so everything that's here ends up over there. So there we have added sodium cyanide to this equilibrium solution. And as a consequence, we've added both sodium ions and cyanide ions. Well, the question is, what effect does sodium ion have on this mixture? As written, the balanced equation. Absolutely nothing. It's a spectator. But the cyanide ion is a common ion to this balanced equation because it fits in right here. So, according to Le Chatelier, if we add sodium cyanide to this mixture, the cyanide ion is going to increase the concentration of cyanide, so that disturbs the equilibrium. And the natural response is for the equilibrium to shift back toward reactants. Now, what does that do for the acidity of the solution? Well, if we recognize that the acidity is based on hydronium ions, so if we add cyanide ions to this equilibrium mixture and shift back toward the reactants, we're going to have to consume some of these hydroniums. So that would reduce the concentration of hydronium and consequently reduce the, actually increase the pH. Reduce the concentration of hydronium, increases the pH. So what does that mean? Before it was at a given pH, and after it becomes more basic. Now that we have that concept in mind, let's define what a buffer is. A buffer, in chemical terms, is any solution that resists a change in pH. If the solution is at equilibrium and we do something to disturb it, it will resist that movement. It won't completely negate the movement, but it will resist a change in pH. Generally speaking, a buffer solution, most commonly a buffer solution, begins with a weak acid. But there are buffers that start with weak bases. Now, why do they need to be weak? They need to be weak acids. Well, this is a good example of a weak acid. So what happens with this weak acid when we put it in water? It makes a little bit of this, but not much. In other words, it produces a strong base. So that's important for the concept of a buffer, because if we have created a strong base from a weak acid, then what happens if you add hydrogen ions to the solution, or hydroniums? They're synonymous in this case. If you add hydrogen ions, that's a strong base, and strong bases are strong attractors of protons. They accept protons rapidly. So when you add a hydrogen ion to this solution, this strong base is going to pick it up and shift back to this position, which means that you have not changed the pH very much with the addition of that acid. There we have a buffer. For the moment, we'll forego the discussion of weak bases and the effect they have, but the explanation is similar. So that's an introductory discussion of buffers as weak acids. Now let's get into some more details before we flesh out the actual behavior of a buffer when we add bases to it.
According to the Chateau-Gay principle, initially in this acetic acid acetate buffer, there is a new acetic acid molecule formed for nearly every hydronium added to the solution. As the added hydronium ions react with acetate ions, equilibrium between acetic acid and acetate ions is reestablished. Only a very small amount of acetic acid ionizes to form acetate ions and new hydronium ions. The animation illustrates this process. Here, a hydrogen chloride molecule ionizes in water. The resulting hydronium ion reacts with an acetate ion, forming acetic acid. Due to small Ka of acetic acid, very few acetic acid molecules ionize to form acetate and hydronium ions.
Okay. So in this example, the description was of acetic acid, which is also a weak acid. And the explanation is exactly the same. because a weak acid, like acetic acid, produces a strong base. The strong base is attracted to protons, and any protons that we add to that solution are going to be snapped up by that strong base, reducing the effect of the addition of those protons.
A buffer solution, like the one on the right, resists changes to pH upon addition of small amounts of acid or base. Each solution here starts at pH 9.25. The solution on the left is not a buffer solution. Click the button to add the strong acid HCl.
So notice what's happening. The non-buffered solution instantly changes pH because we've added protons that are not being absorbed or picked up by any strong base in solution. They're simply there in solution, they drive the pH down. Whereas the addition of those protons from the acid in the buffered solution are being picked up by the strong base and are consequently removed from the reaction mixture. No hydroniums are formed, or few hydroniums are formed as a consequence. We'll keep adding acid and see what happens. pHs continue to decrease, but more rapidly for the unbuffered solution than for the buffered solution. Okay, here's a general problem-solving technique for buffered solutions. In order to determine the pH of the modification that we perform on a buffered solution, we first need to know the stoichiometry. That is, what is the relationship? What's the controlling reaction? And we've talked about that in Chapter 14. What's the controlling reaction for the particular acid-base solution? Then we do our equilibrium calculations. So we have to establish this stoichiometry first, then do the equilibrium. So when they okay, I think we're getting at the addition of base here rather than acid. So if we have an original buffered pH and we add hydroxyls, what do the hydroxyls do? The hydroxyls replace the conjugate base, the A minus, or in this example, the C minus. So we start off with a ratio of unionized acid with the ratio with the conjugate base. And the ratio after the addition is going to be very close to the original. Now that has to do, remember the concept of equilibrium constant versus equilibrium position. The constant's not going to change for an equilibrium, but the position might. And in that case, this ratio tells you that the position has changed, but the equilibrium constant has not. Now, this might be a little out of order, but I'm going to take these slides as they come. There were a pair of researchers whose last names were Henderson and Hasselbach. And the calculations involved in determining a given pH for a buffer were they considered too unwieldy. And sometimes they are, particularly if you have multiply ionized acids, like phosphoric acid, for instance. So they set about solving this problem to simplify it. And the equation they came up with bears their names. And you'll have to forgive this slide. That's supposed to be a double barbed arrow. So if we take this as our acid dissociation, this is a weak acid producing hydrogen ions and the conjugate base. Then we can write an equilibrium expression for that, Ka, which is equal to the product of the equilibrium concentrations of the hydrogen ions and the conjugate base ions divided by the equilibrium concentration of the unionized acid. We rearrange this equation. Why? Because the whole purpose of creating a buffer is knowing the pH that is in the buffer zone, that is, the pH that will be most stable when you add acid or base to it. So we want to solve this equation for the hydrogen ion concentration that will give us that buffer zone. So now that we have the hydrogen ions on one side and everything else on the other side, we proceed to determine what the pH is, and that is the negative log of the hydrogen ion concentration. So here we have the negative log, and we're taking the negative log of the entire equation all the way through. Now that gives us pH on this side and pKa on this side. You're all familiar with that. But we can't reduce the expression here to a p-value because we have two different concentrations. It's the ratio that's important. So we maintain the equation at this level, only with one more modification. And that is to remove that negative. So if you recall, the negative log of any expression like this is equal to the positive log of y over x. Right? So if you change the sign of a log, the log of a quotient, then you flip the quotient. That's all that's been done in this case. It's just a mathematical identity. So what does this say about a buffered solution? What it says is you need to know two things to determine the pH of your buffered solution. One is you need to know the pK of your weak acid. And secondly, you need to know the ratio at equilibrium of the conjugate base and the unionized acid. If you know those two things at equilibrium, then you can calculate pH using this equation. It also says, not only will you know the pH, you will also know that any solution that has this same ratio will have the same pH. So if this ratio is 1 to 10, that would be just the same as 10 to the minus 1 over 1. Or it would be the same thing as, let's take something else, go up the other direction, 2 to 20. So if these were equilibrium concentrations, then your pH, the buffer pH, would be exactly the same. All that matters is that ratio. Now, there are other things to be considered when you choose that ratio. One is, do you need a large buffer capacity? Right, now we're talking about the difference between equilibrium constant and equilibrium position. If you have a larger amount of each of these, your buffer capacity is much greater. It can absorb more acid or more base before its capacity is exceeded. Whereas if you have a small amount with the same ratio, it has a lower capacity. Okay. So that's Henderson-Hasselbalch. Let's see if we can use it. Suppose we want to know the pH of a buffer solution that is 0.45 molar acetic acid. Okay. And 0.85 molar sodium acetate. So it's going to dissociate, and it's going to be C2H3O2, and this is going to be 0.85 molar in acetate. And the Ka for this solution, or for this acid, is 1.8 times 10 to the minus 5. All we have to do is use Henderson-Hasselbalch. Substitute these values in there. We know this one is the Ka value. We know this concentration is 0.85 because that's derived from sodium acetate, and this is from acetic acid, and the pH should be 5.02. Okay, so now let's look at what happens when we add acid. We already have looked at what happens when you add acid. When you add acid to a buffered solution, the A minus, or the conjugate base of the weak acid, quickly combines with this proton based on the stoichiometry and gives you the unionized acid. Absorbing the hydrogen ions nearly maintains the pH of the solution. What happens when you add hydroxyl ions? Right. Well, we know from practical experience that when you add a base to this solution, then the pH doesn't change much either. Changes a little bit toward the basic, but not much. That's the whole point of a buffer. Let's see. Let's go back here. Okay. So when you add hydroxyls, we know what happens when you add more acid. right? It reacts with the hydrogen ions. Okay? What happens when you add hydroxyls? Well, remember what hydroxyls are, where they come from. Okay? the Kw for this reaction is 1 times 10 to the minus 14. Right? So that characterizes water as a weak acid, which means hydroxyl is a strong base. So if hydroxyl is a strong base and we add some other to the solution, can it drive the pH up? Can it make it more basic? Well, if it's a strong base, what's it going to do? It's going to react with that hydrogen ion. So if the hydroxyl and the hydrogen ion react, produce water. So that means no more hydroxyl. And the pH is, again, stabilized. Okay, next item. What are some characteristics of buffer solution? I think I've alluded to it, actually described it already. Buffers usually contain a relatively large concentration of a weak acid and whatever the conjugate base is produced from that dissociation. Added hydrogen ions react with the weak base. Added hydroxyls. Since the hydroxyls react with the weak acid, that's true. That's one way of looking at it. In other words, if we had this one, producing whatever, and we add hydroxyls, then it's going to have a strong attraction to this one and produce more of this plus that. So I think it really doesn't matter how you look at it. Is it going to react with this one or is it going to react with that? My personal opinion is it reacts with that. Because that makes more sense for stabilizing the pH, for removing hydroxyls from solution. Either way works, because when it does this, it makes water and produces some of that, but none of this, right? It only produces that. But if it reacts with this, then it removes that from solution, and we have the same situation. So either way works. Okay, so the pH of a buffered solution is determined by the ratio of the concentration of weak acid, and that should be strong base. I think that's a typographical error, because there's the weak acid, but there's a strong conjugate base. Yeah, that should be strong base. Actually, it should say strong conjugate base. So, give me a second. I want to make that note. Okay. So as long as that ratio remains relatively constant, the pH will remain constant as well. And that's why we use large concentrations. Because in order for the ratio to remain constant, if we have large concentrations, then removing or adding a little bit of each one will make virtually no, and will virtually have no influence on the ratio itself. And here's the discussion of buffer capacity. I've already talked about that. It just means that a large capacity means that the ratio, while the ratio is constant, the absolute amounts of the conjugate base and the weak acid are, the absolute amounts are large. So, the next logical question is, what's the ideal or the optimal pH for a solution? It is the position in the equilibrium where this ratio is most resistant to change. Now, how can we figure that one out? Okay, here's the rule, and I'll explain it to you right after. The pKa of the weak acid determines the ideal pH for the buffered solution. Okay? Now let's see, how much of this am I going to have to draw? In order to describe this, I need to draw a titration curve. And this is what we're going to do in lab also. We're going to actually gather the data so we can draw a curve for acetic acid. So let's say we have our system here, and we're going to have a weak acid, so that means we're going to start off at a low pH, and we're going to start adding base to it, strong base, sodium hydroxide. So this is added sodium hydroxide, which is basically the hydroxyl ion. And this is the pH. So for, let's see, 1, 2, 3. There's 1, 2, 3, 4, 5, 6, 7, 9. And for, and it doesn't matter what the concentration of the acid is. Well, it does matter, but as far as the buffer is concerned, it doesn't matter. It matters because if you start off with a high concentration of acetic acid, that means you have to add more base to get to your buffer pH, right? Because that ratio has to be at a certain point to reach the buffer zone. Okay, so let's say we start adding base, and we're down here in the 2 region. I don't know exactly what it is, and we get these data points, and it starts off low, and it increases to a certain point. Then it starts flattening out, right? And then you reach another point where the pH just skyrockets, and then it flattens out again. So that's typical for a weak acid being titrated with a strong base. Okay. So the various points on this titration curve are, first of all, when you reach this region in here, you actually have neutralized all of the acid. In other words, the acetic acid, CHEM102 of sodium hydroxide yields sodium acetate plus water, right? That's an acid-base reaction, right? Acid plus base yields salt plus water, always and forever. So when we have reached the point where the stoichiometry matches that this is equal to that, and that means all of this has been converted to that, then we're at this point. That's the equivalence point. Okay? Anything beyond that is extra base. So the extra base keeps the pH going way up until it gets to a point where it's got so much base in it, a little bit more makes no difference in the pH. So the curve then flattens out again. But what's down here? Well, in this region, you're at 1/2 equivalence. So what do I mean by that? That means 1/2 equivalence means this concentration and that concentration are equal, right? So we look at the Henderson-Hasselbalch equation, and we have the log of the conjugate base concentration over the weak acid, right? So at that point, we have equal amounts here, right? So what does that mean? Well, in terms of a logarithm, this divided by this, if they're equal, right, that value equals 1. So what's the log of 1? Remember, the log of a number is the power of 10 that gives you 1, right? So what's the power of 10? That equals 1. X equals 0. So at that point, this term drops out. It's now 0, and that means pH equals pKa. So at this point, that pH is equal to pKa. So when you do your titration, you determine what this midpoint is right here. Right, you have a curve and then it flattens out a curve. So you want to find where's the flat section? Where is it not curving? Then you take the midpoint of that and then find out what the pH is at that position. Then you have your pKa. And remember, pKa equals minus log of the Ka. Right? So Ka is going to be 10 to the minus pKa. And you can calculate what your Ka is once you find out what the pKa is. Okay, so this is these slides coming up are going to just explain what I gave you here in block print. The stoichiometric point, the equivalence point, is where this is equal to that. So that means all of this is used up, all of that's used up, and you end up over here.
Hydrochloric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly solvated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
Okay. There's our equivalence point. Now, this slide illustrates what happens with a strong acid and a strong base. When you combine a strong acid and a strong base in equal amounts, you get a neutral solution. We found that out in the last chapter. And this is what the titration looks like. Right? So that's your equivalence point is pH 7. So when you have equal amounts of each one, you've neutralized them, and the only thing left in solution is what was there before, water. Rest is spectators. This is just the reverse titration. Right? So if you have sodium hydroxide, you're starting off at a high pH, adding acid, and you come down the slope to the equivalence point, you're still pH 7. Right? So let's see if we can solve some equilibrium involving weak acid, strong base titration. Remember, we want to start off with a stoichiometry problem where we actually let the reaction run to completion. And it's the controlling reaction. So we got to find the controlling reaction, then we let it run all the way to its stoichiometric end. Then we take the conditions that we determined from the stoichiometry and do an equilibrium calculation to bring it back to the actual pH. It turns out that is a much simpler approach than trying to solve the problem for equilibrium from the very beginning. It's virtually impossible to do it that way. So don't even try. That's my advice. Just do it as a stoichiometry problem first, then take the conditions that the stoichiometry determines at its endpoint, and then go back and work it as an equilibrium problem, which means ice table. So here's an example. Say we have a solution mixing 0.1 mole hydrogen cyanide with 0.04 moles sodium hydroxide in 1 liter of aqueous solution. Okay. So we're going to have HCN, and it's 0.1 mole, 0.1 mole in 1 liter, so that's automatically 1 molar. And the Ka for that acid is 6.2 times 10 to the minus 10. And we also have 0.04 mole of sodium hydroxide. So sodium hydroxide is 0.040 molar, right? Because it's 1 liter solution, moles per liter. So what are the major species? When before reaction, right? Because we're talking about stoichiometry, so we need to know our starting point, right? So the major species are hydrogen cyanide, sodium ions, hydroxyl ions, and water. Those are the major species. Now we say, well, of course, sodium hydroxide is not a major species because it completely dissociates in water. That is your starting position. And hydrogen ions and cyanide ions are not major species because it's a weak acid. So most of it is going to be in this form, practically all of it. So what are our dominant reactions? Well, of course, we got water that we considered. We got hydrogen cyanide reacting with water, right? Okay. Can we say that hydrogen cyanide and hydroxyl react with one another to produce cyanide ion and water? Well, let's see. Hydroxyl ions are a very strong base. This is a weak acid, so that's a possibility. This one's just stupid. Sodium hydroxide is a completely soluble compound. It's not going to be any return reaction there. It's all over here. It's none of it's going that direction. And then sodium's not going to react with water to produce sodium hydroxide. So those two are definitely out. Okay, so how do we decide which one of these is the controlling reaction? Let's see. Oh, okay. So this reaction goes on all the time. But this one has a Ka of a certain value. This one has a Kb of a certain value, which we determine by equals that. So we would have 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 10, right? So we just need to do a quick calculation to find out what the Kb for this reaction is. So let's see, 1 exponent 6.2. So this is 1.61 times 10 to the minus 5. Okay. So the first reaction is 10 to the minus 14. The second reaction is 10 to the minus 10. And the third reaction is 10 to the minus 5. The bigger number wins. Just remember that. That's your rule. The bigger number wins. So we've determined that this one is 10 to the minus 5. That's the controlling reaction right there. Why? Because it's going to produce more of that than either one of these is going to produce on its product side. So that's why the next slide operates on this equation only. This is the controlling reaction. So what are the major species after the reaction occurs? All right. Well, it's still a very small number, right? So that means we're still going to have a significant amount of this left over. But we will have some of this also. And all of this is going to be consumed in the process to produce some of that. So at the stoichiometric result of the equation is to consume all of this, because it's going to be the limiting one, because we're adding base gradually. So at our equilibrium point, we're still not going to be exceeding. Well, we would, of course, not at equilibrium, but at stoichiometric point, we would consume all of that to produce this. So I'm not sure why that one's still there. Let's see, maybe they'll explain it to us. Well, all right. I'm going to have a word with the authors. They let us have a blind alley. Okay, so we learned how to determine what the controlling species is. the controlling reactions. Now they're going to switch gears on us and use acetic acid to actually determine the pH. All right, so let's start all over again. Calculate the pH of a solution made by mixing 0.2 moles of acetic acid with 0.03 moles of sodium hydroxide in 1 liter. All right, so every 1 liter, that means this is 0.2 molar, that's 0.03 molar. And we just need, first of all, what are the major species before you get started? Sodium and hydroxide, they completely dissociate. Acetic acid is still there, water is still there. So we write our major reactions, throw these bottom two out, because they're just stupid. And then we calculate the, we know the pKa of this one, we know the pK of that one, we just calculate the pKb for this one, and I guarantee it's going to be bigger than either of the first two. So the controlling reaction is going to be this one. Right? No, excuse me. Which reaction controls pK? They're saying that this one is. 10 minus 5, 10 minus 10. They're saying that this one controls the reaction. Well, now that doesn't make any sense. Because it was supposed to be the larger one. This one should control the reaction. I think what's going on here is that you don't have a reaction here because there's no base. You've got to have a reaction that includes the base. The strong base, hydroxyl, will remove a proton and give you the conjugate base of the weak acid plus water. All right, okay, that makes sense. But if we try to conduct the reaction with this equation, there's no base. Right? Right, so scratch what I said before. It's not the largest one that controls it. The one that involves a base. If you're going to add base, you've got to have a base in the reaction. All right. So we let the reaction go to completion. Actually, we're going to use an ice table for this one too. So use an ice table for the beginning of the reaction. And you find out that you're starting off with this concentration of acid, this concentration of base, nothing over here. Right? So what's the change? Well, this is the limiting one. It's going to run out. So all of that's gone, and it leaves you with this much at equilibrium. And this much. So now that you know what these concentrations are at equilibrium, you can use Henderson-Hasselbalch. You could do another ice table, sure. And we'll do that one, just to prove that we can. So now we go back to, once we've used up all the base, now the controlling reaction is the one with acid only. We start off with this concentration, right? We have acetic acid reacting with water, produce hydronium and acetate ion. And we know the concentrations to start with. Then the change is we're going to, which direction are we going to go? Well, we've got no acid over here, so that means it has to go that direction. So we're going to add some of this, add some of that in equal amounts. And remove some of this in an equal amount. So there's our expression. We can write our expression like that. And we would have to assume that X is very small. And then we will calculate pH as 3.99. Okay. What if we do it with Henderson-Hasselbalch? We just plug in the numbers. Instead of doing this, we just plug those numbers in here, and we get 3.99. So this shows you two different ways to work the equation and to work the determination of buffer pH. And I vote for the easy way. So here's another situation. So say we start off with a 100 ml solution of 0.1 molar of acetic acid. There. And we want to know the pH. Okay, so remember my drawing earlier, right, where I went like this? That would be our starting pH right here. Right? So, since this is not a buffer, we can't use Henderson-Hasselbalch, we have to use equilibrium. And the equilibrium says if we're starting with this molarity, and the amount doesn't matter, right? That's just thrown in there to confuse you. The only thing that matters is the concentration. So there we have the concentration. There's none over here. We're going to add some, take some away from here. There's our expression. Just work it on down, assuming that X is very small. Then we get a pH of 2.87. So now we're going to take that solution, 0.1 molar solution, acetic acid, and add some sodium hydroxide. Now the amount matters, because now we're talking about capacity, and we need to know the absolute amount that remains. Because we're going to do stoichiometry first, let the reaction go to completion, and then walk our way back. So the stoichiometry of the reaction is the one with the Kb, where you add the base. The equilibrium part of the reaction is where you have just the acid that's left over, and you work your way back to the equilibrium situation. So there's our addition of base. We're starting off with this concentration. Now, why that number? Well, how many moles of acid do you have? 0.1 times 0.1 is, okay, let's do it this way. C2H3O2 and base, right? So the concentration of this one is going to be so many moles divided by the total volume. Right? So if we have 100 milliliters, that's 0.1 liter. So 0.1 molar times 0.1 liters, that's right, equals 0.01 moles. Then we divide that by the total volume, which is what? 150, which is 0.015 liters. So let's see if that comes out where it's supposed to. 0.01 divided by 0.15. 6.67 times 10 to the minus 2 molar. Okay? Then we do the same thing with the base, and it comes out to be 0.0333 molar. So now, the stoichiometry of the reaction uses up all the base, and it has to be zero, right? Because it's the limiting reactant. I'm going to use it all up. We're going to have this left over as the acid and this left over as the base. And then we're going to use Henderson-Hasselbalch because it's quicker and easier. So we plug in the concentrations that were determined here. There's your conjugate base. There's your conjugate acid. Now that's not the controlling reaction. Those are the concentrations. The controlling reaction is the one where the acid reacts with water. Right. So don't get confused. This is the stoichiometry. It's not the equilibrium anymore. this equation is the equilibrium. And the pH now will be 4.73. Now, is that in the buffer zone? It's not part of the slide, but it's an interesting question. So if pH is 4.73, is that in the buffer region? Well, how close is it to the pKa? Right? So the Ka is equal to 1.8 times 10 to the minus 5, and minus log of the Ka equals minus log of 1.8 times 10 to the minus 5, which is equal to 1.8 to the minus 5. Take the log of it, and then change the sign. 4.74. So that solution gives us a pH that's right in the middle of the buffer zone. It's ideal, perfect. Okay. Let's see. Didn't we just work this problem? Calculate the pH of solution at the equivalence point when 100 milliliters of 0.1 solute. Okay. All right. So this, we'll leave that there. This problem now is not what I'd consider an equilibrium problem. This is a stoichiometry. This is pure stoichiometry. So the equivalence point is that point at which equal concentrations of acid and base are there. So the total volume, in other words, we're going to have to find out how many moles of acid are there. All right? So we did that up here, 0.01 mole. If we have 100 milliliters of 0.1 molar, so we have 0.01 moles of acid. Let's see, and a total and 0.1 molar sodium hydroxide. Right? So what's our concentration going to be? Well, let's do it like this. And this gives us, let's see, sodium acetate plus water. Okay, so we're starting off with 100 mils of 0.1 molar, 0.1 molar, 100 milliliters, right? And we determined that that would be 0.01 mole. Okay? Sodium hydroxide, we're starting off with 0.1 molar. And we want to know what the pH is at the equivalence point. So these are equal concentrations. That means equal volumes are required. Right? Because the stoichiometry is 1 to 1. So for every one of these, you need one of those. You have the same concentration, you also need the same volume, because you have to end up with exactly the same number of moles of each one. Right? So that tells us the total volume. 200 milliliters. Okay, we have 200 milliliters, or 0.2 liters. And before the reaction occurs, that is, now that we know how much is in there, the concentration of each one of these, before we go that way, is 0.01 divided by 200. So that's 0.05 molar. Okay? So that's why when we set up this reaction, and there's our sodium hydroxide, and there's our acetate ion. So they've just taken out the sodium ions as spectators. It's the same equation. So we're going to start off with this and this. There's nothing over here. Both of these are going to cancel each other out, 0, 0, and we're going to end up with 0.05 molar acetate. After the reaction. Okay? Now, what reaction are we going to have? Well, we don't have any more of this in there. No more acid. Right? So we can't have an acid equation. We have to have this one reacting with water. Right? This one's going to react with the water. Right there. Because there's nothing else there. So this weak acid, this is actually a strong base, is going to strip a proton off of water and give us the weak acid, and that's a mistake right there. There should be no charge on that ion. I think after I've been through these slide sets so many times, I recognize that thing. There, there. Any more? Yeah. All over the place. Okay. So what's that going to do? Well, this is going to strip a proton off of water, give us the acetic acid without the minus sign, and hydroxyl. Okay? So here's the change. Right? We're going to lose one of these. We're going to gain one of those and gain one of those. And this is the equilibrium situation. Okay? Now, we can set that up to be, we need to know the kV first. Right? We calculated the kV before as 10 to the minus 10. Right? Because this is the strong base reacting with water, not the acid reacting with water. So the strong base reacts with water, we need to know the kV for that reaction. So we just take the Ka and divide it into Kw. 10 to the minus 14. And we get this value. Now we set up our equilibrium expression. That times that divided by that. And roughly 0.05. So that means the X is this value, molar, and the X represents OH. So if we calculate the POH, then we can find out the pH by subtracting it from 14. And the pH should be 8.72. Any questions? Okay, we'll move on. So, this is the titration curve that I drew on the board not too long ago. And you'll notice we determined what its starting point was. That's actually a little high. It needs to be down here somewhere. But the buffer zone is right here. Notice the pH is not changing much. Right? pH is here. So the pH doesn't change much in that region. And the ideal position is right in the middle at 25 milliliters, because 50 milliliters represents the equivalence point. Half equivalence point would be right here. Okay, I'll let you eyeball that while I'm erasing the board. Okay. So these are various theoretical weak acids, well, plus one strong acid, a couple of strong, one strong acid, and weak acids with various Ka values. So this is just illustrating the fact that the Ka for this one, the pKa for that one would be about 2, exactly 2. So that means half equivalence point would be right here. Half equivalence point for this one would be 4. Half of this one would be 6. Half of this one would be 8. Half of this one would be 10. Right? So if you want a weak acid ideally suited for your buffer pH, you want to pick the correct Ka for that acid. Now, this just illustrates the point that you don't have to have a weak acid to have a buffer. So ammonia is a weak base, and if we titrate the weak base with a strong acid, we get sort of an inverted titration curve to the one that you would see for a weak acid and a strong base. So we start off at a high pH for ammonia, and we add acid, and the equivalence point is right here at 50. So the half equivalence point would be here at 25 milliliters, and there at about 9 is the pK for ammonia. So what would that mean? Well, if we have ammonia and we're adding acid from hydrochloric acid, then it's going to produce this one. Now let's see, how about like this? That's proper. Put my plus in the right place. Okay. So you would you have a Ka or a Kb for this one? Well, actually, the controlling reaction would be that. No, that would be the equilibrium reaction. This is the stoichiometry. That's the stoichiometry. We'll produce so much of this and so much of that. And then we'll get, this is our base, this is our conjugate acid, and then you would have base over acid in our Henderson-Hasselbalch equation. You need the pK for this, for the reaction with water. And that would be our pH. I'm not going to throw that one at you. We'll just stick with weak acids because they're the most common. That was just to illustrate the point. Now, remember in General Chemistry 1, we did a titration to determine the molar mass of citric acid. And rather than use a pH meter, we used a color indicator, phenolphthalein. Well, we didn't talk about it then, but the fact of the matter is, indicators undergo their own little acid-base reactions. And when they reach a certain point in their reaction, change colors. So that's how we know that we're near the equivalence point, is because the indicator is usually a weak acid. Not always, but a weak acid or a weak base. And they undergo their own acid-base reactions right alongside the reaction of interest. So what are we looking for? Well, we have to iron out our definitions. When you do a titration curve, and you have the equivalence point, that is the exact point at which stoichiometry is complete. But if we're going to use an indicator, we can't necessarily say the equivalence point, because the indicator might change color down here, or it might change color up here. Because the amount of base added hasn't changed very much from here to here, it's not a serious problem. I mean, the pH, the equivalence point might be, I don't know, 8. And then if this is 8.5, or this is 8.2, then it doesn't matter. If these are the pHs at which the color changes and we see it, then the fact of the matter is we haven't moved the base very much to see that change. So it doesn't have to be, the color change doesn't have to be exactly at the equivalence point. And we call it the end point. Wherever it happens to be is the end point rather than the equivalence point, just to make the distinction between equivalence versus when does the color change. Okay? So here's for phenolphthalein. That's not supposed to be blue. Acid is supposed to be clear. Right? So there's another mistake. And it should be clear. Pink is right. No, wait a minute. That's not right. Neither one of them are right. The one that's on the pink side should be, let's see. Wait a second. Under acidic conditions, right, the left-hand side should be clear. The right-hand side should be pink. Okay. That should be pink under basic conditions because this is going to be dominant. And under acidic conditions, you're going to have a lot of these. We're going to add a lot of these. They're going to pick up those and make this. So this is going to be clear, colorless. Right. Okay, it's right down here. This is the basic form or the pink form, the indicator negative. And this is the, we call it the protonated form. The one that exists when there's a lot of acid around. Okay? But that's not even the right structure. There should be a proton right there. You work on this slide. Okay. So what's the Ka of this reaction? Right? The Ka of this reaction, but the Ka is 3.9 times 10 to the minus 10, but the pKa is 9.4. So 9.4 is where the phenolphthalein, if this were a phenolphthalein titration, that would be 9.4. Right there. Now, what can we say about the ideal indicator range? Well, now we're getting out of the realm of we have to introduce human physiology. The human eye can detect a difference in concentration of about 10 to 1. So that means it's either 10 times this concentration to that one, or 10 times this one to that one. So that's a pretty wide range. It's like 100. 2 orders of magnitude it takes the human eye to see the difference. Right? Fortunately, that's not a problem. But what does that mean in terms of the pH change region around the pKa of our given indicator? Okay, so we drag out Henderson-Hasselbalch again, and we find out, all right, where's that pH for the pKa? Well, it could be anything. Right? The pKa could be, we had an absolute value for phenolphthalein, but it doesn't matter. Whatever indicator you have, you want to know the pKa, and then you want to know the ratio of the conjugate base to the acid, the weak acid that is the indicator. Okay? So with this expression, if we say the conjugate base is 10 times the acid, then we have 10 divided by 1, which is 10, and the nature of logs is 10 to the first power is 10. So that means this expression is 1. So pKa plus 1 is 1 pH into the pH range. Or it's the other way around, 10 to 1 is 1 divided by 10 is pKa minus 1. So what that means is the pH range that is most suited for your particular indicator is the pK for the indicator plus or minus 1 pH unit. Right? So if we go back, let's see, the pKa for phenolphthalein is 9.4. Plus or minus 1 pH unit. So it has a useful range in a titration of between 8.4 to 10.4, plus or minus 1. Okay? Now, that's a rule of thumb, right? It depends on what color it is, also, as how sensitive the human eye is. So, that explains the theory behind the ideal range of pH for an indicator. But the chart actually has practical information in it. Some indicators are only good within a much narrower range, and some of them are good, and you can detect color change in a broader range. So the best way to handle it is just find yourself a chart like this, right? And there's the indicator. There's its ideal pH range, right? So let's see, we should be down here. Phenolphthalein would be right in here, right? So it's right in there. In fact, it doesn't go up to 10, right? Up to 10 is too high. So plus or minus 1 is an idealized range. These are the true ranges based on empirical evidence. And that is buffers. Happy spring break.